Alright, here we are with lesson 15, using unique triangles to solve real-world and mathematical problems. So let's take a look at example 1. A triangular fence with two equal angles, angle S and angle T, is used to enclose some sheep. A fence is constructed inside the triangle that exactly cuts the other angle into two equal angles. Therefore, angle SRW is equal to angle TRW. Show that the gates represented by SW and WT are the same width. So what parts of the triangles correspond, if any? Well, two pairs of angles of equal measurement, angle S and T, and angles SRW and angle TRW, and one pair of sides of equal lengths, shared side RW. So is there a condition of unique triangles that is being satisfied? Well, yes, the triangle satisfied the two angles and the side opposite a given angle condition. So based on this condition, what can we conclude? We can conclude that SW, the segment, or in this case the gate, is equal to WT, or that the gates are of equal width. Alright, example 2. In triangle ABC, AC is equal to BC. John says that the triangle correspondence, triangle ABC corresponds with triangle BAC, matches two sides and the included angle, and shows that angle A is equal to angle B. Is John correct? Alright, so I'm going to go through this and highlight the sides that we are talking about. So if for some reason you missed the highlight, just rewind the video or reverse the video and play it back again. So we are told that AC is equal to BC. In this case, this side on the left triangle and the right side of that triangle on the left. So AC is equal to BC. The correspondence, triangle ABC is corresponding to triangle BAC, tells us that line segment BC corresponds to line segment AC, and line segment CA corresponds to CB. And also that angle C is equal to angle C, which means that triangle ABC is identical to triangle BAC by the two sides and the included angle condition. So here we go. Here is CB, the right side of the left triangle, corresponds with line segment CA, the right side of the right triangle. And AC, or CA, on the left triangle corresponds with CB on the right triangle. So again, if you need help seeing that, then go ahead and rewind the video. Also, we are told that angle C corresponds with angle C. So that's why we have the two sides, 1, 2, and the included angle, and they match for both. Since we've already made the distinction that these sides are equal on both triangles and the included angle, that means both triangles are identical. So from the correspondence, we can conclude that AB, here's triangle A, or angle A, it corresponds with angle B on this triangle. They have to be equal also, and therefore John is correct. Alright, exercise 1. Go ahead and take a look at this on your paper, but I'm going to go ahead and demonstrate what is being explained. So Mary puts the center of her compass at vertex 0 of an angle and locates points A and B on the sides of the angle. So again, just to remind us how we use the compass in this matter, you can go ahead and use your compass to spread this apart, and notice that if I were to draw from point O I would get an arc at B. Okay, just like so. And she did the same thing, not changing the length or the width or the distance between the point. The same thing is used to mark point A. Now I'm not going to go ahead and do that. So basically what it's saying is the line segment OB is equal to the line segment OA. All right. Then what they did to get point C is, again, not changing the compass. She put her compass point on B, which I'll go ahead and show you, and then drew an arc mark. She could have gone wider, but she knew that they were going to cross somewhere here in between. And so she's got an arc mark there. And then from point A, she does another arc mark that's going to intercept the first one. All right, and so that's essentially how they got point C. Now mine is off a little bit, but that, if this was precisely measured, then point C is where both of these arc marks cross each other. And so then what she did was use the ruler and draw a line originating from angles O that goes through, or a ray in this case, goes through the intersection of those two arcs, and that she called point C. So just a little bit more of an explanation as to how this was created. So now we want to explain why BOC is equal to AOC. Well, if you think about it, if we drew a line from BC, then this line would actually be the same, because we said that the angle or the compass length wasn't changed at all. Then that means that this length here from A or OB is the same as the length from BC. And also, if we draw a line segment that connects AC, then that line segment AC is also equal to OA. So if we have two triangles that are being cut here, then what do we know about BOC, BOC, and AOC, AOC? Well, obviously this has to cut this in half, because we have these sides and this side, and this side is also the same. So this is by the side, side, side condition. So corresponding sides mean that we're going to have two identical triangles. So let's go ahead and switch back over. Since Mary uses one compass adjustment to determine points A and B, just like we said, OA is equal to OB. She uses the same compass adjustment from B to A to find point C, which means that BC is equal to AC. The side OC is common to both triangles, so triangle OBC and triangle OAC. Therefore, there is a correspondence that OBC is corresponding to OAC, and that matches 3 pairs of equal sides. So since we know we have identical triangles, therefore we know the angles BOC has to be equal to AOC. All right, the next exercise, you'll see you have a kite on your paper. So the quadrilateral AB or ACBD is a model of a kite. And again, I'm highlighting AC is equal to CB. And again, if you miss it, back up the video and watch it again. And also AD or BD is going to be equal to AD. So I've got that highlighted in red. You also notice that the tick marks, the single and double tick marks, indicate that the sides are equal also. So now the diagonals AB and CD, and notice that I'm putting this in blue, represent that the sticks help keep the kite rigid. So the blue highlighted lines are our diagonals. They cut across the kite and join the two corresponding angles. All right, so let's start over. John says that angle ACD, so watch this, ACD, all right, so that's this angle right here, is equal to BCD. So I'm doing this in blue, so BCD. So ACD is equal to BCD. Can we use identical triangles to show that John is correct? All right, so let's see if we can do that. From the diagram, we see that AC is equal to BC. All right, highlighting it again. AC is equal to BC, and AD is equal to BD. So we have two sides that are the same. Well, if you notice, CD, which I just highlighted in white, is a common side to both of these triangles, ACD and BCD. So therefore, there is a correspondence. Triangle ACD is the same as triangle BCD. So here I've kind of overlapped it with blue and red. So both of these triangles have to be the same based on what? The three side conditions. So that matches three pairs of equal sides. The two triangles are identical by the three sides condition. All right, so let's take that off. So from that correspondence, then we can conclude that ACD, and I've done this in yellow, so the arc for ACD is equal, and here's the yellow arc for BCD, so therefore John is correct. All right, part B. Jill says that two sticks are perpendicular to each other. Use the fact that angle ACD being equal to angle BCD and show what you know about identical triangles to show that angle AEC is equal to 90 degrees. Now you're going to have to refer back to your triangle and try to figure this out because I'm not going to give you any hints on this one. So since we know that AB is equal to BC and an angle ACD is equal to angle BCD, that came from part A, and we also know that triangle ACE and triangle BCE share a common side, which is called CE, we can find a correspondence that matches two pairs of equal sides and a pair of equal included angles. So the triangles are identical by the two sides and the included angle condition. Therefore, we can conclude that angle AEC is going to be equal to angle BEC, and since both angles are adjacent to each other and they are on a straight line, we also know that they must equal 180 degrees. Well, if that's the case, then that means that both angles have to be 90. If they are both the same, that means one can't be more than the other. Therefore, two equal angles, 90 and 90, have to equal 180. All right, for part C, John says that Jill's triangle correspondence that shows the sticks are perpendicular to each other also shows that the sticks across at the midpoint of the horizontal stick. Is John correct? Well, since we have established that triangle ACE and triangle BCE are adjacent to each other, we know that line segment AE is equal to BE. So this means that E is the midpoint of AB by definition. All right, go ahead and try problem 3 yourself. Go ahead and continue the video when you are finished. All right, you should be done with problem 3. And here's what you should have. So in triangle ABC, angle A is equal to angle B. And that is noted right here. So here is ABC. We'll consider that the first triangle. A is equal to B. And Jill says that the triangle correspondence, triangle ABC, is equal to triangle BAC. So A, B, C. This is the order we're going in, so we have to go in the same order. B, A, C. Matches two sides in the included angle and shows that AC is equal to BC. Is Jill correct? Well, if A is equal to B over here, then the correspondence tells us that A is equal to B over here. So A on the left triangle is equal to B on the right. And B on the left triangle is equal to A on the right. So therefore, and also that AB, this line segment on the bottom of the left triangle, is equal to BA, the line segment on the right triangle. So therefore we have two angles and the included side. Two angles and the included side in between those angles. So from the correspondence we can also conclude that AC, over here on this side, AC, is the same as BC, which would be on this triangle. So therefore Jill is correct. Since we have identical triangles, now we can say that any line segments or any other angles are the same. All right, exercise 4. Go ahead and complete this and continue the video to check your answers. All right, you should be done with exercise 4. Go ahead and compare your answers to the answers here. If you have any questions, make a note and bring them to class. All right, so let's wrap this up. In deciding whether two triangles are identical, examine the structure of the diagram of the two triangles to look for a relationship that might reveal information about corresponding parts of the triangles. This information may determine whether the parts of a triangle satisfy a particular condition, which might determine whether the triangles are identical. And be sure to identify and label all known measurements, and then determine if any other measurements can be established based on the knowledge of geometric relationships. So having that list of triangle correspondences is going to come in really handy as we work through this unit. All right, we'll see you in class.